Welcome back. We're going to talk about Newton's law of universal gravitation today. We're going through the grade 12 physics syllabus from Queensland in Australia. This is unit 3 and we're still in the first topics, which was all this classical physics, and today we're specifically talking about gravity. So there's the orbital mechanics topics from our syllabus that we're going to go through, and we're going to go look at the first couple today, the first two of them in this one. So to get your mind thinking, unlike that guy in the little GIF there, think about how gravity actually works on your body. So for example, in those first two there, think about the first one. Can you stand with your back flat against a wall and touch your toes without moving your feet? So as in you're leaning up against the wall there, your back's up against the wall. Can you bend over and touch your toes without moving your feet? A little bit similar to the second one there. Can you sit upright in a chair with your feet on the floor at the front of the chair and stand up without leaning your body forward, keeping your body upright the whole way? What you generally find in these scenarios is that your center of gravity is too far back from your feet or too far away from where your feet are supporting your body, which tends to overbalance you. Don't do what that guy did there, run into the post. It's not funny. Okay, today's tasks. We're going to have a look at gravity. We're going to understand gravitational forces between masses and how Newton's described this with an equation. There's an equation there, so obviously there's going to be some calculations that we're going to have to deal with as we can describe what's going on. Firstly, there's a nice little video there to give you a bit of an understanding how gravity is developed. I'll try and link that in the comments underneath there. You can check that guy out. But gravity, what actually is it? It's a universal force of attraction between all objects with mass, and that's the key part there. They've got to have mass. And what we're interested in is how far away these masses are from each other. So the magnitude, of the gravitational force between two objects is determined by the mass and the distance between their centers. And that's the important part, between their centers. Not just how far away they are, how far away their center of masses are from each other. Like if you can compress the entire bit of mass of that whole object down into one single point, where would that point be? And how far are those 2 points away of the two objects? So increasing mass will increase the gravitational force, and increasing distance will decrease the gravitational force. Notice how we've written our proportionalities there, how they work with each other. Now, here's how Isaac Newton first sort of described it back in 1687 language. I deduce the forces which keep the planets in their orbs must vary reciprocally as the squares of their distances from the centers about. You got all that? What are we saying there? A reciprocal arrangement means a 1 over the square of their distance, and he's talking about in proportion with their masses as well. So what does this tell us? It tells us that there's this force of gravity, and it's going to be in some way proportional to 1 over the distance squared, but also the two masses, that type of arrangement. Now, the easy way to get rid of a proportionality is to add a constant, and that's what we'll do when we make this simpler. So here's our formula here in the red box. So the force of gravity is the Fg. We've got two masses on the top of our equation here, which we've listed there, the big M and the little m. That's the two objects and their mass, obviously in kilograms. The big M tends to refer to the object with more mass, and the smaller m is the one with less mass. So if it's, say, the force of gravity between you and Earth, the capital M would be the mass of Earth, and the lowercase one would be yours. But if they're two objects of the same mass, say we're looking at the force of gravity between two protons, then both m's are the same. Our r squared, it's an inverse square relationship, is the distance between the centers of the object in a straight line. And our new little constant we're introducing here is big G, as opposed to little g, which is like acceleration due to gravity, which we'll come back to next episode. Big G is just this proportionality constant. It's the universal gravitational constant, as we've written just there. All right, it's this number that sort of helps us work out forces of gravity in all objects in the universe. So obviously we call this a big G because it's a capital one, as opposed to the little one, which tends to be acceleration due to gravity. This is the value of 6.67 by 10 to the negative 11, worked out experimentally. We don't really need to worry too much about that. Notice the units. it's a force, so it's newtons for a particular area and a particular mass. All right, you can have that's how the constant comes out. So long as you're using standard SI units for everything, you should be right. As we can see in our diagram there, we've got two masses, a big M and a little m, which is these two here, and we have a particular distance they are apart, the radial distance, and we have a force here. Now, if we think about my next question there, in which direction do the forces act? So if we consider this object here, it has a force that is acting in that orientation, and the other mass is acting in that orientation. So the forces are in the direction that an object in mass would move or would accelerate. All right, so the arrow tends to point the way the force is moving towards the other mass. In this scenario, if the two masses are the same, then they're going to be equal forces on each other. Particularly, it always works that way. In fact, no matter how my equation here works, all right, it is the force on each object due to the other one. So the force on the big M due to the little m is the same as the force on the little m due to the big M. The force of gravity between you and Earth is the same as the force between Earth and you. All right, they were both the same. How do we know it's a vector quantity? Because we have a magnitude and we have a direction. Oh yeah. And this is not necessarily applying to larger objects or anything more. It is the same force between those two objects. The significant note here is that Newton could explain this quite well. He's written the formula there quite well, but he couldn't really explain a bit why it's actually occurring. And this is not uncommon in physics. We'll often work out how something operates. We'll work out an equation that describes it perfectly, but we won't necessarily know the reason why it's actually occurring. Similar to my little example there, we knew for a long time when tides would occur and when the high would happen and when the low tide would happen. And it took us a little while longer to realize it was due to the gravitational attraction of the moon on the water on Earth and the water sloshing around as a result of that we're seeing as the tides go up and down. So that's a case where we knew exactly how to predict the tides well before we knew what was actually causing it. A couple of examples there you might want to look at. What's pulling on what? What's nice challenge questions there, worth having a discussion with somebody else. There's a nice little FET simulation there. Again, I'll try and put the link to these FET ones down in the bottom in the description to give you a bit of a go at something like a practical example of this. Okay, time for a quick question. Which of the following is not true of gravity? Number one, it is responsible for our weight? Yes, it is responsible for our weight. It's a force of attraction between two masses. So there's a force involved, F equals ma, and the a in that one is the acceleration due to gravity, which we call the little g. So that one's true. Anti-gravity forces do not exist. We've found no evidence that anti-gravity would exist where this force is working opposing a force pulling them together. If you think about electrical forces, you have positive forces and negative charges. So think of a positive and negative would attract, but two positives would repel, two negatives would repel. So that happens. We have north and south poles in magnets, but as far as gravity is concerned, we've only ever seen it as an attractive force. So anti-gravity, on our current understanding, does not exist. There's no evidence for it. Number three, it provides only an attractive force. Well, yes, that's what I just said. It only attracts between objects with mass. So that only leaves us one last solution. Number four, you're weightless in free fall. So, yep, number four, in free fall, you still have force of gravity is mass times gravity acting on you. All right, and it's just causing that acceleration that is pulling you towards the Earth. However, you're in free fall, so you don't feel anything pushing against you. There's no normal force, so you yourself don't feel your weight. You just appear weightless, even though there is actually the weight that you have. Okay, let's look at an example of our equation. So part A there, calculate the force of attraction between Earth and the Moon, given that the Earth-Moon distance is that. So we have one mass, another mass. It's a calculate question, so it's going to be numbers that we plug into our calculator. We have a distance, so we've got to work out the force of attraction. and then determine the order of the magnitude of the force. Okay, so we know what calculate means. So we've written down our variables that we know. We know the mass of the two objects. All right, notice that the small one is the moon because that is a smaller indice than that one there. So that one must be the big one, which is Earth. Got a distance. We've got our universal gravitational constant and our nice little formula. So we plug everything in. Notice that our distance here doesn't necessarily take into account the center of masses. I'm going to come back to this point in a minute, but typically the distance is between the center of masses, and we're not really accounting for that because in this scale it's not making a huge difference. But all of our numbers plug into our formula just there, and it goes into our calculator, and it all comes out in the wash. 2.03 by 10 to the 20 newtons is the force between the Earth and the Moon. So determining the order of the magnitude, this is something that's kind of added a bit more in recent times, all right, is 10 to the power of 20. It is that indice there that we're writing down is the order of magnitude, all right? Typically in these scenarios, there's several ways to think about this. That 2 is quite a small number. Usually if it's under root 10, we tend to ignore it, ignore that number there, and then only look at this scientific part here, the times 10 to the power of 20. All right. Sometimes you might think, well, if it's a 5 or greater, you would round up and the indice would go up there to 21. But typically root 10, if the number's underneath that, then we can pretty well ignore it. Most of our examples in this course tend to be that. So if you ask the order of magnitude, you're literally just writing down that whatever comes after the times 10 bit, that bit there. Righto. Think about our distances. These things can be small versus large distances. Think about a small distance, like say 2 protons and so on, and their distance away from each other. Typically, if they're within one diameter of each other, it's the strong nuclear force that dominates massively, and I'm talking like 1,000 times more strength, more force than gravity. But when it's talking about larger objects like our Earth and the Moon example here, all right, there's a good example of how far away they tend to be. If the Earth's circumference is about 40,000 kilometres, the Moon is 385,000 kilometres away. The separation is around 9.5 times the circumference of Earth. It's a way of sort of working out how far away they are if you wanted to draw a rough diagram. You can work out this last point here. How many diameters away would that be? It's just maths. We'll work that one out for you. All right, so again, we do have to be conscious of this bloke here is standing here on the surface of the Earth, but we're really interested in how far he is away from the center of mass of the Earth, which has this radius of the Earth that we need to factor into all of our calculations. So here we go. Determine the force of gravitational attraction between the Earth and a 72 kilogram person in an aeroplane at this altitude. Note how we've written it out there in 10,000 meters and scientifically, same thing. Now, so we're 10,000 meters or 10 kilometers above the Earth's surface. We're going to add in, the radius of the Earth over here into that R squared number that we're going to put into our calculation, and it all goes into our same formula. Formula doesn't change. So determine just means it's a calculation where we kind of work out something afterwards. It's a force of gravity, so it's going to be some sort of vector quantity here. Oh yeah. Writing down what we know, we've got the mass of the Earth, the mass of the person, we've got the distance above the Earth, the radius of the Earth, and both of those we're putting together to give us our R value that goes into our equation down here. Notice that's the same number there. Everything else is the same. 2 masses in there, all in kilograms. Our big G value is in there as well. It all goes into your calculator. It all comes out in the wash. All right. The force is for 704 newtons. All right. And it's a gravitational force between the person and Earth and between Earth and the person. All right. Let's take this a bit further. Here's an example of how gravity works over much, much large distances. A lot of the other fundamental forces of the universe, of the strong force that holds like protons together in a nucleus, or the weak force that causes radioactive decay to occur, or the electromagnetic force of like positive, negative charge attractions and so on, tend to operate really well over shorter distances. Gravity is a lot less magnitude. It's a lot weaker, but it operates over massive distances. So in our universe, what we've worked out is there's this thing called the Great Attractor, where it appears to be everything is sort of attracted towards in our local area of the universe. We don't really know what it is. If you look at this diagram here, you can see where Earth is on that little diagram, and each dot on that diagram there that forms those white lines you're seeing is a whole different galaxy. So that represents an incredibly huge number of galaxies. If we look at our other diagram here, there's the Milky Way, and we're all being attracted towards this point over here. Now, the problem with this is we don't really know what's there. Now, why is that an issue? We don't really know what's there because it's for the most part behind the Milky Way. So there's the center of the Milky Way there, that disk that we exist in. See how it's got those dark patches through it? That indicates there's a lot of dust and so on there that limits and obscures optical light, like light that we can see. We have the Great Attractor here, which for the most part is behind much of the disk, so we don't really know what's attracting everything to that point. It's kind of a bit of a mystery these days. All right, a little bit more about some relationships here. Don't forget, we do draw information as graphs, so it's important to understand what's on a graph. All right, you often see these sorts of questions on the external exam. Typically, in these sorts of scenarios, you could be asked to interpret a graph. Think about this one on the left-hand side. It's force versus distance. You can't just read this number off as 8 because you have to include it's 8 by 10 to the negative 6 newtons. All right. You can see it's an inverse square relationship. The challenge for you is relate that back to the formula. Why is this an inverse squared relationship? And if you look at the formula, F is proportional to 1 over r squared. That's what we've drawn here in this graph, and now it's linearized. Gives us a nice linear graph. Why would we want to create a linearized graph? Because we weren't going to want to find the gradient from 2 points on our graph, work out the gradient of this. What's it going to be? Go back to your equation. What's our equation? Force of gravity is big G m over r squared. So if I have force and 1 over r squared, it's like if I rewrite this, I'll just move over. Right, that's my y variable there. That's my x variable there. The gradient equals big G times the two masses. All right. Hence, we can work out either of those. If we know what the objects are, their masses, we can verify big G. If we know one of the objects, we know what big G is, we can verify the mass of the other object, and so on. Not too concerned with the y-intercept. Generally, it's a representation of the experimental error in whatever experiment is we're using. If we think about this proportionality, if our little cloud there, if you double the mass of the satellites or double the mass of the planet, the force between them will double. Is this true? All right, it's effectively doubling something on this side because its proportionality is going to double that over there. All right. Another little challenge question for you to have a look at. Why don't you pause the video and try that guy out. There's another little PhET simulation for you to have a look at around gravity and force and so on. I'll try and put the link down underneath. All right, a few more little questions. When you add brass masses to a spring balance, why does the spring stretch as you add more mass? All right, basically as you're stretching the spring, it's increasing the gravitational force. All right, even though the mass of the Earth is constant, the mass on the spring is increasing, which will increase the force of attraction between it and Earth. Is the stretch proportional to total mass? Look, it's for the most part, stretch is proportional to force, but obviously we start to run into the limitations of how springs work. A few things to keep in mind. Don't forget about when we talk about this radial distance, this r value that we talk in our equation. We have objects that are quite far apart, and it's easy to think in terms of this distance here versus the distance from their center of masses. There are times where you can get away with using just the distance between the two objects, but often adding in that extra radius there makes it a lot more accurate, and obviously you do that on both sides. It's red over there, it's a bit hard to see. So over long distances, that extra radius of the planet doesn't really matter, but it's more correct. Don't forget, our quantities are often given in non-SI units, non-metric system units. When you've got this sort of scenario here, go back to standard units, meters, meters per second, that sort of stuff. Ensure that you can plot this force versus radius and you understand what it looks like, and you can linearize it by doing that little scenario there. And if you do one of those PhET simulations I linked to, you'll get some data and you can chuck it into Excel to do it for you. All right, quick question for you. Which of the following is not true about the gravitational force between two objects? Doubles when one of the masses is doubled. Yep, we saw that was true. Quadruples when both masses are doubled. All right, so think about our equation. If we double both of these, 2 times both of these, this guy here is going to be 4 times bigger. All right. It obviously is proportional to big G because if we look, F, oops, I can't write. F is proportional to big G. There's no squareds or fractions or anything between those two, so they are. Does it halve when the distance is doubled? Nope. This is an inverse square relationship. When the distance is doubled, it will be a quarter of the force. So number 3. Right, a little challenge question for you there. Thinking about circular motion that we've discussed before. Why is it easier and quicker to send a probe to a planet away from the sun rather than towards the sun? Have a look at that little video there. I'll try and put the link down below. Essentially, if you think back about your circular motion, we're talking about an object in constant circular motion about another object. There is this massive sideways velocity that we need to overcome. So even if we put a force that way, it's going to fly off to the side still. The video will explain more about that one. That brings us to the end of most of what we want to discuss today. We've ticked off our 2 little objectives there, 3, sorry, understanding what gravity is in our formula. We can describe what gravity is and how it works. We can do some calculations now, which is our first 2 on our syllabus that we need to check off. So, brings us to the end now. It's your turn to practice. Have a look at the first section of the next book, the next chapter section, so you understand what's coming. All right, because obviously we haven't spoken about this guy yet. We're going to start talking about that one next. All right, thanks a lot for coming and see you next episode.